Okay. Very good morning to one and all present here. It's my privilege. It's my privilege to welcome you all for this 5 days online ATL FTP on artificial intelligence and machine learning. So I welcome Dr. Prasant Kumar Ghosh, Associate Professor, Department of EE from Indian Institute of Science, to deliver the title on deep learning for automatic speech recognition. So it's my privilege to welcome you all, and then I hand over the session to Dr. Ramya for introducing the speaker's profile.
Yes, thank you, sir.
Hand over to you.
Good morning, one and all. I welcome to the day 4, session 2 of our Faculty Development Program on Artificial Intelligence and Machine Learning, being organized by MVJ College of Engineering in association with AICTE Teaching and Learning Academy. Now, let me introduce our guest speaker now, Dr. Prasant Kumar Ghosh. He is currently working as an assistant professor in the Department of Electrical Engineering, IISc Bangalore. His professional and research interests are in the area of research in human-centered signal processing, engineering model and technology development with applications to education and healthcare, silent speech processing, and so on. He holds a BE in Electronics and Telecommunication Engineering from Jadavpur University, Kolkata, and MSc in Engineering specialized in signal processing from IISc Bangalore in 2006. He received his PhD in signal processing at Signal Analysis and Interpretation Lab from University of Southern California, Los Angeles, USA in the year 2011. He is the recipient of many awards like Professor Preeti Shankar Teaching Award for Assistant Professor 2017 from IISc Bangalore, Pratiksha Trust Younger Investigator Award for 2017 from IISc Bangalore, third place in Signal Processing Cup in the year 2015 and 16. Competition was organized by IEEE Signal Processing Society. A CBR Startup Research Grant for Young Scientists in Engineering Sciences for the year 2015 from Department of Science and Technology, Government of India. Inspire Faculty Fellowship Award for the year 2012 from the Department of Science and Technology, Government of India. Honorable mention for the Best Paper Award for the year 2010 and 11 in HMH Department of Electrical Engineering, University of Southern California. And also MHI PhD Scholar for the year 2010 in MHD of Electrical Engineering, University of Southern California. Center for Excellence in Teachings Award for Excellence in Teaching in the category of Electrical Engineering for the year 2010 in the University of Southern California. Best Teaching Assistant Award for the year 2007 and 2008 for graduate class in University of Southern California. Best MSc Thesis Award for the year 2006 and 7 in the Electrical Engineering Division at IISc. He won the first prize in Mr. BRV Vardhan Postgraduate Student Paper Contest organized by IEEE Bangalore section. He is the scholarship holder by MHRD, Government of India. He has published more than 150 research papers in the journals like IEEE Transactions, ACM, Elsewhere, etc. And he has filed 4 patents. He has been invited for chief guest, session chair, and talks in many international conferences, workshops, and FTPs from IITs, NITs, and various institutes of national importance. He has given more than 30 talks so far. He plays a role as an associate editor of an Elsewhere journal of computer, speech, and language, and he has also been the reviewer for various IEEE transaction journals. It's really an honor and pride to have you with us today, sir. I heartily welcome you to the session. We welcome you, sir. Over to you, sir, now.
Thank you, Ramya. I hope you can hear me. Thanks for the nice and kind introduction. And good morning to you all. Good to see you be present in a large number, virtually at least, right? So a few checks before I start. I hope you can see my screen well, full screen mode, right? And then let me just go back and forth once and tell me whether you can. I hope you can see this changing slide. Can you
Yes,
confirm
sir.
that?
It's in full
Okay,
screen. It's visible, sir.
okay, excellent. So welcome you all to this topic and the 1.5 hour talk on deep learning for automatic speech recognition. So as um, Ramya pointed out, I'm from electrical engineering department at ISC, and we have a lab called Spire Lab. And I'd like to, before I go to the core topic of the talk, I just want to introduce all of you to the place where I come from, right? In particular, the Spire Lab here. So you can just Google it, Spire Lab, and then you'll reach this page. We have a varieties of activities that are happening, research, development, and teaching, all academic activities, and also a lot of interaction and collaboration with many industry and academic partners. So just to give you a glimpse of the Spire family, here is a quick snapshot, but taken, of course, last Jan, 1 year, right? We all know what's happening over last 1 year. So we are all working virtually, and it is good to see back these pictures at least, in touch virtually. I must tell that this Spire family is highly dynamic, right? So there are a lot of interns, project assistants, and of course regular PhD and master students part of this lab and contribute to the ongoing activities of the lab. So what do we work on? We work on a variety of problems, but all of them are related to signals in a way or the other generated from human body. Right? Starts from speech, all the your head motion, your motion of the articulators, and then for example your snore signal, cough, right? A lot of signals and rich information that this human body generates, primarily to target for applications where we can decipher critical information from these signals. For example, can we tell from your cough signal whether you have asthma or not, right? Or from your speech whether you have Parkinson's or not, right? Things like that. So a variety of problems starts from fundamental research questions to applications and all the way up to development and real use cases. So we have always this ongoing effort, and if you're interested to know more or interested to join the team, you're always welcome to drop an email to me or to this Spire Lab email ID, spirelab.ic.ac. Okay, so with that, I'll now move to the topic of the talk, which is deep learning for automatic speech recognition. So I'm sure you have been now over this last couple of days before you have been exposed to what is deep learning, right? Because this workshop is sort of thematically around that. Now today we'll be introducing this, or in this talk we'll be introducing this term automatic speech recognition. Right? Before I go to the technical definition of it, I thought that I'll give you a flavor of what are commercially available automatic speech recognition. Right? So, I mean, I'm sure many of those you're using today, right? For example, if you start with Google Now or Google Voice Search, right? Or Amazon Alexa or Microsoft Cortana, right? All of that are, widely used. And there are many more from Nuance, from, many other startups within India and abroad. So, and this is just a really growing market. A lot of companies are coming because today almost all the devices and all the interactions are tending towards becoming voice assisted. So you want to speak and communicate. So it boils down to the core requirement of how machine can understand, and really by understand I mean first convert what you speak to a textual form, and that's what speech recognizer is. And just to give you a sense of how growing the market is for this technology, I just want to show you this specific note, which is not very old. It is May 2020, like 6 to 8 months before, where Alibaba declared that they have invested $1.4 billion just for generating, doing research and development on this voice assistant AI. So, so a lot of opportunities for this, and it is a right time to get into the ASR or automatic speech recognizer. I'll be keeping on using these two terms, ASR and speech recognizers. You know, um, um, uh, interchangeably. So if you have any difficulty, please type your questions here and we can take as we go along, but I'll pause in between somewhere and then we can take few questions at that point, and then of course at the end. Okay, so let's now ask what is ASR, right? So as I just said, we start from this raw speech signal. So for example, you record with a microphone and store it as an MP3 file, right? So that's your input to the ASR. And we expect the ASR to spit out the text, generate the text, which says, do you understand me, right? For example, that's the text being spoken here. So so the entire talk today is about understanding this black box, which is written as ASR. But of course, in the title, as you saw, deep learning for ASR, right? So what is deep learning here, right? This is a black box that we're trying to understand, how it converts the raw speech to the text. So deep learning is somewhere out there, right, at the bottom, as you see. I hope you can see that part of the screen. If you can't, please put a note in the chat. So how are these two connected, right? By deep learning, I mean you already must have covered, right? Starting from neural network to deep neural network to convolutional neural network to recurrent neural network and its variants like LSTM and many more complex networks that has come from the domain of machine learning and artificial intelligence, right? So that's all that lies in this deep learning layer. But we have a requirement of the ASR from raw speech to text. And I want you to understand this slide very well, right? So that you really get to the context. So, typically if you look at ASR, this has a long history. It started in 1970s, I'll say. And there have been, today, if we look back and see what are the approaches, there are essentially two approaches. One is traditional approach, and that is called end-to-end approach. So traditional approach is primarily, I'll say, conventional or old. And the end-to-end is very recent, like few years, just it has started. So this traditional approach is in some way gives us the knowledge to go and develop the end-to-end approaches. So under the traditional approach, here is a summary, quick summary of how the different layers within the traditional approach lies. So it starts with figuring out what kind of acoustic features we require for doing this ASR, and also understanding of the speech sounds or phones. And then once we know these two, we go to the statistical speech recognition, which really establishes the problem of ASR on a firm ground of probabilistic theory. And I'll say from there are two main themes. So there are a lot of variants, but two main themes. One is what is called GMM HMM, and this is called DNN HMM. If you don't understand them now, that's fine. We'll be going through them in due course. And then on the other side, under end-to-end approach, which is pretty recent, there are several components there as well, starting with connectionist temporal classification, CTC, and sequence-to-sequence approach. I'll come to all of that in this talk, and then combination of both of them, right? CTC and NLP. Well, so that's the kind of summary that you have, an overview of this entire ASR, research and development that has happened so far. And some of this actually went into Amazon Alexa or Google Voice or Google Now. So what is deep learning here, right? So the deep learning is right here. So deep learning comes as a powerful learning paradigm in some of the components of this ASR. In the end-to-end approach is essentially the entire approach that is built upon deep learning, but in the traditional approach, the DNN HMM in particular, and its variants, there are some variants, which are supported or bolstered by deep learning, right? So I hope this gives you a picture as to how deep learning is connected to ASR. And what we'll do now is that we'll try to cover this overview at varying depth. I must tell you, this itself is a full semester course by itself. So we can spend, let's say, 40 hours on this, right? So there is so much information. So what I have done for your information here is that I have gone through this entire flow, but I have given you enough references and links to papers, tools, databases, so that if you understand or get a sense of this talk today, and if you're interested, you can go through the slides, which I'll certainly share with Ramya. Then you can go through those references and learn more. Because within this 1.5 hours, we won't be able to cover this entire, rich set of information and components, right? So okay, so let's start with this block. Let's understand it a bit, right? So as I said, it's a black box you can begin with, which takes a raw signal as input. It could be audio samples denoted by X, right? And it outputs the transcription of the sequence of words, right? That's W. So there is a function, right? Some function that this black box performs, take raw audio samples and outputs the speech signal, outputs the word sequence. Right? So let's just get some sense of how difficult it is. So that's the whole purpose of next two slides. So how when I say how difficult it is, it simply boils down to the following. Let us say you speak this sentence. Do you understand me? Suppose you speak 10 times. You can record with your own laptop or phone, and then you measure the length of it. You see that every time you speak, the length is different. Every time you speak, the waveform, as you see here, the plot, they look different. So every time you speak, they generate different set of samples. So there is a variability in the samples as you speak the same set of words multiple times, right? Then next comes the variation in the speaker itself. So when the same sentence is spoken by another speaker, of course that is supposed to vary, right? There are other speakers with different voice characteristics, the speaking rate, and many other factors. Next comes in what environment you are speaking. Right? So it could be an environment in an open road or in a silent office, or it could be under a running fan. All of that will add noise, right, to the different amount of noise to the signal. And according to the signal will change, other samples will change. Of course, we are all speaking the same set of 4 words. Do you understand me? And more importantly, context. For example, if I speak this sentence, do you understand me, right now, and suppose you don't understand, and I explain again, and I try 10 times, and you say, still I don't understand, then I may be speaking that in a different way, depending on the context. Say, do you understand me? Right? So it changes the whole waveform and the samples again. So there are many, many factors that changes the way we speak the same set of words, to be honest. And that's true for any set of words, right? Anything. And more than that, right? So there are many, many other factors that come into play and that changes the sample values. And that's why for the same word or same sequence of words, there can be zillions and millions of speakers speaking in different conditions, different contexts, and so on and so forth. But all of them are speaking the same thing. So as a human, when you hear all of them. Do you understand me? But machine, no, machine can't do it. So the question is, how do we make machine to do that? So the environments in particular that are challenging or contribute to these challenges are audio quality, of course, right? Whether you record in MP3 format or some other codec. I think there are some background noises, so please mute your mic. And then a distance from the microphone to the speaker, right? If you are really far from the microphone, the kind of signal you get is echoey, right? Like what you have at the end. Then background noise, reverberation. So there are many, many factors. So overall, it makes this ASR is a very complex. So I hope you appreciate now that it is not a simply, sort of string matching problem. So the samples of the audio keep on changing depending on what you speak, where you speak, right? So that itself is a big challenge. So of course, we'll as you see that today we don't have a solution for all of this, to be frank. So for example, if you see, let's say if you take Google SR, Google Voice, or let's say Amazon Alexa. Suppose you record right in front of a drilling machine. You're speaking, and I don't think it will be able to record at all, or rather understand you at all, right? Because the drilling machine noise is so much. So it boils down to many other factors. So today we don't have one machine or one device, gadget that can understand you at any condition, anyway. So that you have to keep in mind. So we are always under some restricted scenario we develop this. A few other information here. This is also known and also termed as text-to-speech (STT). and just many variants, and enormous amount of research has gone into the variants. For example, keyword spotting. It's not like ASR. For example, I'm speaking this in an entire talk for 1.5 hours, let's say, and you want to find out what are the places I spoke ASR, right? ASR is a keyword. ASR. So you want to find out only that. Not that you have to recognize the entire 1.5 hours, but only recognize or find out where I've spoken ASR. Or for example, it's a voice command, right? For example, you can say, "Hi Alexa," right? So the Alexa understands, so that's a voice command recognition. And of course, the main and the most intriguing topic today is this large vocabulary continuous speech recognition. When I say large vocabulary, it means you can speak any set of words from a large vocabulary, right? We don't speak anything and everything. We have a set of vocabulary. We don't really go beyond that. For example, you unnecessarily don't speak about any medicine names, right? So depending on the domain, the vocabulary changes. But here when you say large vocabulary, it covers a set of words that are typically used in the in the regular context, let's say, for our generic purpose. And it's continuous speech recognition, so it is not that I say, for example, in the first bullet, I don't say also known as speech, right? I don't give gap between that, right? It's running speech, also known as speech to text. And it causes enormous amount of complexities. Like, for example, I can tell you, let's say, say I eat, right? If you say I and eat, these two are two different things. But if you say I eat, I, that E of I and E of eat, they get mixed. So you say I eat, right? And it sounds a different thing because you know what I'm speaking. You know the context, you know the words you recognize. But it's in language you won't be able to recognize, right? So these are all challenges, and these are some informative points. Okay, so now, given that we now understand what ASR is and the challenges, let's now move to description of this. So I'll try to go as much detail as possible, but I'm sure time will be a factor. So we'll be now talking about the acoustic features, right? So what are the acoustic features? The acoustic features are those set of numbers that represent the raw audio samples, right? You saw the plot. So these acoustic features are a substitute for them. So you derive them from the raw signal. Listen to me again. You derive them from the raw signal, and then you feed these features into the ASR block, not the raw audio file, correct? So we have to make sure that when we extract these features, they have to capture the useful information, right? They can't be capturing only noise. For example, the noise is there. They have to capture useful information, but also same time, it should be robust and resilient to the background environment. So it will be great if we have features which capture the speech specific information very well, but not the other non-speech components, right? But it's given, it has to be computed from the signal itself. So, the history of acoustic features for ASR, again, is long, right? It all starts from understanding how we produce speech. Right? So, as you know, we have an entire organ that is dedicated for speaking, apart from eating and respiration. And lung is a very important component there, right? So, lung pushes the air and that goes to your trachea, and then voice box and the mouth. Nose, right? And when they go out, because of the modulations and shapes of your mouth, it makes different sounds. And all these articulators like tongue, jaw, lips, velum, they all contribute to this, time varying, noise at the background. So it will be great if. Okay, so the output is the final speech sound. And this speech sound typically has frequencies, as you see, from a few hertz to 8 kilohertz, typically. But of course, you have some people having sound or frequencies beyond that as well. Then, on the other hand, when we hear, our hearing has a wider range from 20 hertz to 20 kilohertz. So we not only hear speech, but many other sounds, right? So speech is one of the things that we hear. So we now get a sense of what is the frequency range of speech, right? So a few hertz to 8 kilohertz. Now, if we consider this on the right hand side, what you see is a raw waveform, right? It is directly captured from microphone and passed through a to D converter, and then you get essentially an array of numbers, one-dimensional array of numbers. Of course, it depends on the number of channels. It can be mono or stereo, then it become multiple channels or multiple dimensional arrays. And then the sampling rate will determine how many samples you get. Number of bits will determine the size of the number of bits per sample, determine the size of the file. And overall, the bit rate will be determined by sampling rate times precision times the number of channels. So that's about the bit rate of an audio. Okay, so now when we extract these features, I know conventionally, if I look back, earlier 70s or 80s, people started thinking, well, we as a human here, right? So we must be extracting some features. So why don't we motivate our machines to compute features like that? So there have been approaches to compute features motivated by human hearing, right? This reference, for example, you see there are various features they talk about for this speech recognition, and we'll be talking about them in a bit. So we'll be talking about a particular feature in detail in this talk, and you'll see that it has been motivated again by human hearing, and the feature is called male frequency capture coefficient. But apart from that, there are many other kinds of features using digital signal processing tools and techniques to represent this raw waveform into quantitative numbers. So now let's understand about this one feature which has, I'll say, dominated this entire ASR research over several decades. Right? Even today, people use MFCC for these traditional approaches. So here are the 7 steps for computing MFCC, and I think it is worth knowing so that it gives you a flavor of the signal processing involved in computing. So it starts with pre-emphasis. So here is a summary, right? As you see on the right-hand side diagram, the signal goes through something called pre-emphasis, then framing and windowing, then you compute Fourier transform of that using FFT, and then pass them through Mel filters and compute their log energies, then pass them to DCT, discrete cosine transform, and then compute differential features. So let's go through them one by one. What is pre-emphasis, right? So what happens if you record your speech for a second and then take that as a signal and compute FFT, right? I'm sure all of you know what is FFT in DSP. So you compute that and plot it. You'll see that most of the energy is on the low frequency, not at the high frequency. But there are information at the high frequency. So by pre-emphasis, we try to emphasize the high frequency, right? So by emphasizing, I mean the relative gain of those high frequencies go up, so that the computer gives almost equal importance to both the low and high frequencies. Right? So this is how it is done. This is a simple difference operator with a weight alpha, and that's called pre-emphasis. Then once that is done, then you come back and start framing the signal. What does framing mean? Let me go back here. So this is the output of pre-emphasis, right? Then what you do is you take small chunks. So suppose this one-dimensional array has 10,000 samples. You can take first 200 samples, right? That's your framing. So why do we do that? Because we keep speaking different sounds, right? As I said, I eat, right? So I spoke A, then E, and then T, right? 3 things, I eat. And then if you took small segments, then you don't have 2 sounds in it. You'll have only 1 sound. So if I compute some spectrum, FFT, it will be only related to that sound. So it will be representative of that. So it's called quasi-stationary assumption, that you take small segments and assume them to be stationary. Now, I see questions. I mean, you can use, I'll talk about the end. You can use many features, including wavelets, many techniques, okay? But this, so far, MFCC has been the sort of the standard and performs very robustly and well. Now, once you frame this, right, you get this fixed length segment, like 200 samples, then 200 samples, like you have this non-overlapping 200 samples. And then how do you determine this length of the segment, right? Should I take 200 samples, 2000 samples? So typically, if you look at, every sound like R, E, and T like that, so the range of them varies from 5 milliseconds to 100 milliseconds. So a typical choice in ASR is to choose a 20 millisecond frame. Now, depending on the sampling rate, that length of number of samples will be constant. But in time, in seconds, you capture only or use only 20 millisecond segments. After you segment, you window it, and by hamming or hand window, right? Why is that? Because if you don't do that, there will be an abrupt change at the boundaries of the segments. So you typically use a smoothing window. If you plot this, it will be a very Gaussian-like window, so that at the boundary of the frames, it has a very small value, so that it doesn't cause sharp changes at the boundaries. So typically, what you do, as you must have seen in the previous frame, previous slide, you have 20 millisecond chunk, but you don't take non-overlapping chunks. What you do is you take 20 millisecond and then do a 10 millisecond shift, so that there is a overlapping set of chunks. And then if it's 10 millisecond shift, then you'll get 100 chunks approximately in 1 second, because there are 110 milliseconds in 1 second. So after you do the windowing, you end up getting, if this is a signal and you do windowing, you end up getting several windowed signals, right? And then you perform what is called DFT or FFT on those chunks, and what it returns. So this is the first chunk and the corresponding first magnitude square of the DFT, right? And second chunk, second. So like that, you have bunch of stack of this DFT vectors, and those together are called the this entire operation is called the short. It gives you a three-dimensional picture, right? So you see, it's a 3D because on this axis you have time, in this axis you have frequency, and vertically you have the amplitude, right? So these are the three-dimensional pictures. So you create a matrix in some sense from single-dimensional, one-dimensional signal. So one dimension to I'll say 2 dimension, or rather, if you plot, it's 3 dimensional, right? So now we have blown it up. We have created an image, you can say. So if you take that matrix, what you saw here, right? X, K, F, right? K is the kth window, a chunk, F is the frequency, and X is this value. And plot that as an image, right? So you take a small chunk here, compute its FFT, and plot here, and so on and so forth, like that, right? Everywhere. If you do that, you get a picture here, and that's called spectrogram, right? This is the magnitude spectrogram, which is nothing but magnitude square of the FFT. And as you can see in this spectrogram, this is the low frequency, the high frequency, and the time axis. You see, most of the red color, which are the really high values, they typically come in the low frequency. So speech by itself has a lot more energy in the low frequency, and that's because of our organ that generates the speech. So we are right here, right? We generated the spectrogram after FFT, and then we perform what is called the MEL filters or MEL filter bank, right? So what are they? So these are motivated from human ear. So the way we process the speech signal is essentially through our cochlea, act as a set of filters. You can call it filter bank, and they're all band pass in nature. And interestingly, these filters approximately can be shown to be like this, meaning the filters which are at the low frequency, this axis is frequency, and this is the gain axis. The filters which are at the low frequencies, low center frequency, they have very narrow bandwidth, but filters which are at the high frequency have wider band. So that is sort of linked to somebody put a question on the web there, right? It's something similar in that trend, but here we specifically use human auditory system motivated filters, so they closely match with the human auditory system. So instead of being all uniform with bandwidth, the bandwidth varies with the increasing center. And then you pass this spectrogram, or that you take one column, which is one of this XKF, right? And you multiply these filters. Then within each filter you have some FFT values, and you square and add them up. That gives you energy within that filter. Right? But before I tell you that, I'd like to tell you what is the relation between this MEL filter or MEL scale and our regular Hertz scale. So MEL scale is the scale that you see in the human auditory system, in particular the cochlea. So the difference between the MEL and Hertz is a linear scale, but the MEL is a logarithmic scale, and they are related by this formula. So if you, for example, put let's say 9 times 700, which is 6300, right here, will be divided by 700 is 9. So 9 plus 1 is 10. So 10 log 10 will be 1, right? So 6300 Hertz will go to 2595 MEL. That's how it is related, and the inverse can be easily found. right? So it gives a curve. You can plot it and check. It's a logarithmic. So as I said, now under each filter, you have some effective bins, and then square them up, compute the spectral energy under that filter, and that will be the energy from that filter. So let's call those energies by mj for the jth filter. Then you perform the DCT, right? So when you perform DCT, you get the DCT coefficient. So that gives you the ith MSC. So this is a male frequency Kapström coefficient. Now, why you call it Kapström? It requires you to understand what is Kapström, by the way, but it essentially called Kapström because it perform a DCT on the log of its spectrum or spectrogram, and that's why it's called. Traditionally, Kapström is meant for that. Okay, so once you have this MFCCs now, after DCT you get these numbers. So from a small chunk, you get this MFCC coefficient. So how many MFCC coefficient? It varies, but typically the choices are 13. So for example, I take 200 audio samples and then only convert it to 13 values, C0 to C13, C12, C0 to C12, right? 13 values. And that's a huge amount of compression. And it is shown that these 13 values can really preserve this information, what is there in these 200 samples, or 20 milliseconds, right? Depending on what is your sampling rate. So, and then people have went further and found that if you compute the difference between, or rather you find out what is the change in this coefficient. So let's say if I now denote the C T plus N as the MFCC as at the T plus Nth frame, then I can compute at the frame T what is called DTF feature, DTF is called delta features. Essentially, it's taking the two MFCCs in the frame before and after and subtract them. So that will give you how much change in MFCC has happened. So that's called the dynamic features. And they have found the delta features are very useful. Same is true for the double delta features. So you compute delta of delta, right? So these are also features. So MFCC with cis delta and delta delta are sort of standard in traditional acoustic speech-based ASR. So did people not try any other features? Of course. Why? Because MFCCs are not, it's very efficient, you can compute it very fast, but it's not very robust to noise, and it changes depending on the noise, and that's not good. You want noise robust features, right? So people have tried many others, gamma tone filters, perceptual manipulation, and with deep learning, the people have completed even more different kinds of filters. Right? So, and there are references here. If you're interested, you can explore all of that and find out what are the features. Okay. And of course, with deep learning, people have done a lot more. They have used CNNs, RBMs to figure out features in a supervised as well as unsupervised. Right? And we'll talk about the end-to-end later. You'll see that features are learned automatically already. So I hope that gives you a sense of what acoustic features are, and how they are crucial to represent the raw waveform, right? So we don't use raw waveform to the ASR, but rather compute acoustic features. So for each segment, we compute a feature, right? MFCC delta delta. So it is a sequence of, so for each chunk, you get a MFCC with delta delta, and you keep on sending the sequence of MFCC and delta delta to this ASR. It's a matrix that finally goes. It's called MFCC with delta delta matrix. Now let's talk about speech sound. But by the way, you must saw that. I mean, you have already seen it, right? Deep learning also in some way goes and sits in acoustic features, right? But they're sort of connected to this end-to-end part also. So they did not really connect deep learning here. So deep learning can even connect to the acoustic features, but the network has to allow, or the approach has to allow deep learning. Okay. So now let's go to these speech sounds or phones. So what are speech sounds or phones? If you go to Wikipedia, for example, and that's a correct definition of phone, it's distinct speech sounds or gestures, regardless of whether exact sound is critical to the meaning of word. So a sound that is relevant for your speech, whether it creates a meaning or not. For example, I can say, this is a sound, and we use the sound for saying school, right? But by this sound itself won't have any meaning. Or for example, if I say, ooh, I mean, in some contexts, it makes meaning, right? For example, if you touch fire and say, "Oh, I got hurt," right? So sometimes it makes meaning, but need not be making meaning. It's just more of set of sounds in speech, right? You don't speak the alphabet, and you don't speak the alphabet as it is. You convert them to sound. For example, when I say I speak two sounds, and E, right? Not for one alphabet. But for example, also when I say C-A-T cat, that becomes sound ka, although the character is C. And I say kite, K-I-T, kite, that then also I say sound ka, right? Kite. So cat and kite, C and K, both sounds at ka. But is more like language specific. So in Hindi, we have set of phonemes. In English, we have set of phonemes. But you can think of collecting all languages, all phonemes, and make a big repository. So for simplicity, let's think of all speech sounds across all languages, a big bucket, and that is set of phones. But phonemes are important for meanings. For example, it can change meaning in a word, right? For example, the sweet. You see, when I speak sweet, I'm speaking sa sound, we sound, we, right? Then E sound and T sound, sweet. But if only one phoneme, this is called the phoneme, the sound, it changes to yeah, right? Sweat, yeah. Then it becomes a different meaning altogether. So you change one phoneme, it changes the meaning. So why do we need phonemes, by the way? What the hell we need this for? We need it, as you see in the slide, that we need it critically. So for example, let's say I have a word called Arti, right? So suppose I speak Arti and I get this waveform. Let's say one of you speak Arti, it gives this waveform. Somebody else speaks, it gives this waveform. You see, the waveform keeps changing, but every time everybody is speaking Arti. So if it was a sort of a fixed information or fixed set of values for Arti, then it would have been very easy, right? So for example, if it was, think of this color, right? Suppose whenever Arti is spoken, a red color is shown. Then every time Arti is spoken, it will be red. But that's not true for speech. If it was as simple as colors, then you could have just do a color match and it could have been done. And you found out what word it is. But in the case of waveform, they change drastically from one person to another. Then you imagine to tell computer, if I just give this three and tell this computer, okay, you have three examples of Arti. Now anybody speaks now Arti, can you figure out? Of course not, because the fourth person will have a different set of features and waveforms and everything. So for each word, then we need to have how many sets of recordings and tell that to computer, right? It's going to be very challenging, right? And there are so many words. So how do you even figure out that? Very, very difficult. And how do you even get these recordings? And for example, I mean, we have to go and ask people, speak Arti, speak Arti, speak Arti, right? It's like embarrassing. And then you say, well, speak Apple, speak Apple, speak Apple, report everybody. It's like too much. Right? How do you take care of this? And that's where the concept became, well, do we have to operate at the word level? Can't we do something better? And that's where the phone comes handy. So how does it come handy? Right? So let's take an example, right? So let's say this is Arti, and I have another word called Ardhar, right? Now you see, in Arti, you have this set of phonemes, let's say, or phones, let's call it for simplicity, it's a collection of all phonemes. So this Arti has this phonetic transcription. So A, R, T, and E, right? So these are the four sounds. And here you have these many sounds, right? Ardhar. But what is interesting is that the sound A appeared so many times, although these two words are spoken. So the idea is now, that means if I let people speak normally, we can actually go and figure out what are the places A occurs. And then those will be, there will be many, many A's now, right? Even if I speak, let's say for 1 minute, I don't have to really speak A 10 times, but I'm sure because of we're speaking many, many words, this A sound will appear in many, many words. So that way you'll get many examples of A. And then you can tell computer, well, now see, there are so many examples of A. And so it's a more natural way, right? You don't have to really tell people speak Arti 2,000 times, but you'll automatically get A for 2,000 times. So this is called the shared representation from multiple words. But the phones are critical here, right? You get representation for the phone because the words can be written in terms of the phones. So here is an example of a 39 phone-based English phones set based on alphabet symbols. And then, of course, if once you come up with this, phones, as you can expect, for each word we need to have a phonetic transcription. That if I have to speak this word, what is the right set of phones? Of course, also as you know, one word is spoken in many ways. Right? In English, it is not, but in Indian context, it is, right? So for example, same word, same English word spoken in different native language people. For example, my name Prasanta, right? a Bengali person, I'll ideally speak as a Bengali, I'll speak Prasanto. But let's say somebody from South will certainly speak Prasanta, right? Not O. So the text is same, but the phoneme at the end is A versus O, depending on who is speaking. So this table is needed, right? It's a huge table. For all words, you need to have this done, right? And it's an enormous task, this lexicon preparation. How do you do it? So some linguist, somebody who knows language very well, they can only tell to speak this word, you have to speak out these phonemes or phones. Right? And for some words, there can be multiple repetitions. So this is called phonetic dictionary or lexicon. So this dictionary and lexicon has to be prepared, and that's certainly required to figure out which words, for example, has a sound, right? But looks like we are there, but it is not really solving the problem. Why? Because you see, when I said aardvark and arti, right? It's a running speech. So I didn't say arti, right? I didn't say like that. I spoke arti. So how do you know what is the beginning and end of a in arti? Or what is the beginning and end of a in aardvark? That's not easy. And who will even listen? So you can listen and maybe mark it, right? But you think of it's enormously difficult. So how do you find out these boundaries between phonemes? That's it. And more importantly, this the signal can take different forms depending on where you speak, who is speaking, and that boundary may keep on changing. Many things changes that. So speaker space of speaking, style of speaking, and many variables that contribute. Right? So now, more importantly, as I said, what you speak also gets influenced by what you spoke. The one before, like I it. Now you think here you'll get I and E of it. So it has two things, two sounds, right? E and T, like IT, it, as right? Two sounds. So the question is, when I say I it is merged. I it. There is only one E. It, I it, right? How do you put boundaries here? It's becoming tremendously, so depending on the context, things got merged. So finding boundaries is a big challenge. And many other factors, including the dynamic nature of the speech, right? So how do you overcome this problem? So they say, well, it looks like when you speak a sound in a specific context, maybe that can be. For example, when I speak E in the context of R and T, that sounds like it. That E will be different from if you say whiz, right? That E in context of U and S is different from the E in the context of R and T. So what you speak before and after a particular phone, color that phone, change that characteristic of the phone. So why don't you do the following? Why don't you go ahead, if there are 39 English phones, let's take a phone, put all possible contexts. So it will be 39 square, correct? For each phone, you get 39 square, 39 on the left, 38 approximately, 38 square. One of the 38 here and there, and then you say, I think those are called context-dependent phones. So they are called the triphones, right? Context-dependent. So maybe people thought, okay, that means the right way, because then you have less amount of influence of the context, which is very critical. Right? And you can, of course, put context for other things also, but this is called the triphone. Now remember this. There are also diphone, right? There are two you can think of, but triphone is the most used one. So now we have come from phones to triphones. So a phone in the context of mobile phones. Still not there. I'll tell you why. There are still challenges posed. I mean, it is enormous. Even today we have challenges. Okay, so there is no end to it. So what are the challenges? So first is homophones. For example, still STL and STILL, we have the same set of sounds. So if I just say still, you have no clue whether I'm speaking the first word or the second word. They're called homophones. Right. You already know that. How do you figure that out? There came the development of the called language. For example, I can't say the boy or the boys steal the books, right? I can't say this still. It has to be this still. So from the sentence, you figure out this has to be STL, not STIL, right? For example, say I write poems. So it can't be this right. So isolation is very difficult. So only in context, that's captured by language. We'll talk about briefly. So language model now plays an important role. But how do you bring all of this into this? So you're just learning now what are the factors that complicates the whole story. But how do you bring them in? Just hold on. Then, of course, there are many other problems like phoneme substitution. So instead of saying pin, you say pen, right? And it becomes a different word altogether. Or your accent changes it, right? For example, you say schedule. Somebody says schedule, somebody says schedule, somebody says schedule, right? Many variants. And then, of course, there are real world factors. So, for example, you say, well, I went to the I went to the clash. It's not the clash. I went to the class, right? So you figure out from the context that he has made a mistake. It should be class. So all of this makes search. I mean, it's a search, right? So you tell computer, for Arti, you had this many examples. No, that's not possible. For R, you have this many examples. We don't know the boundaries. It's a challenge. It varies depending on the context and many other factors. You're going to triphone and say, well, for this triphone, we have this many examples. Then all of these other homophones, incorrect phone substitution, all of that make the task even more complex. So it's truly complex, truly. So I want you to appreciate the challenge. Okay. So that's sort of done, right? So you got a feeling of what is phone and why they're used. Now let's move on and see what is statistical speech recognition. Also in that context, what is HNG and how do they come useful here, right? So when you talk about statistical speech recognition, if you look back, like early 1990s, right, or 80s, that time people are doing exactly what I said it right? So think of this. Suppose I want to have a digit recognition, 0 to 9. So you ask 30 people to speak 0. So you have 0, 0, 0, 30 samples stored. You compute MFCC for each of them. So you'll have MFCC matrix for 0 from the first person, second person, like that. So you have a bank of MFCC matrix for zeros. Similarly, you can do it for 1s, 2, 3, all the way up to 9. Now somebody comes and speaks a digit. Can you say which digit it is? So what do? You match. So what this test time, a person came and spoke, let's say 4. The length of this 4 won't be same as any of the one that you have in your training data, right? Training data meaning this 30 times 10, 0 to 9. So you have to now somehow come up with a time alignment between what you want to search for and with what the training data, right? That requires you to use what is called dynamic time modeling. That was a great development at that time. People thought that solved the problem, but of course it's not continuous speech. Isolated words or triphone, you can probably do it, right? But as you see here, right, what I just said, training phase and the testing phase, template matching using VW will give you the records. But is it now solved? No, of course not. How do you know how to compute the distance? What is the distance? Right? Do you do Euclidean distance between MFCCs? Or how do you even choose template? So I told you 30 people. Who are these 30 people? Suppose I take all 30 people from Karnataka. If I now go to Alaska and get a person, do you think that 0 or 1, whatever digit that person speaks, will be close to the corresponding digit spoken by all the Karnataka? Right? It's the people who are changing. So what will be the template? How do you choose a template? So that became an enormous problem. So people started thinking about this is not the right place. This is not the right way to go. So you have to come up with some sort of learning from this large variability of examples. It has to be probabilistic, because suppose I get an example from Alaska, from North America, from Asia, from Japan, but how about people in between? If you have a way to interpolate in between, that can be only done by probabilistic population. That will help us to learn. For example, if I give you points and ask you to fit, draw a Gaussian function on it, right? It looks like the function is Gaussian, but in between you may have missing values. But you say, well, it looks like Gaussian, right? So you fit that to the data points, and you feel that yeah, it makes sense. So that's where this statistical and probabilistic approach came, and this is called statistical sequence recognition. Why? Because the input is a sequence of MSCC features, and output is a sequence of words. You have to recognize an input sequence and generate the sequence of words, right? Sequence of acoustic features, X as input, and words are output. So as you saw in the top, you see speaker want to speak a set of word, right? It thinks linguistic formation of the word, and then speech is produced. Right? Now, speech recognizer does the exactly opposite. Take the speech or the features, there's the X, and then pass it through sequence recognizer or statistical decoding and give these words, correct? So now let us see how we can do that probabilistically. So here is the crux of the, almost all ASR that you see, whether it's a traditional approach, latest approach, anytime, right? So this is a strong or the key take-home slide of this entire presentation. You have to understand this. So see, somebody gave me this X, and I have to find out that word which is most likely for that given acoustic. Let's again repeat that. So somebody gave me a recording, and I can compute two acoustic features in a sequence. That's the X. So now the question is, given this X, can we figure out from our training data which word is the most likely fit for this acoustic feature sequence? Now, how do you compute likely? How do you compute score for likely? Right? So here comes the probabilistic function. So you compute a likelihood score. So you say, well, find out that word from your entire training corpus. V star is the vocabulary, right? All the words, such that this likelihood is maximum. So if you have 100,000 words, 1 lakh words, let's say, I give you a radio, recording, and you have to now go back and say, okay, for this first word, I had so many examples. Can I do a search or map? Find out what is the likelihood. Like that, keep on doing for 100,000 words. Then probably it will be 1 week by the time you can tell the right answer, and it may be wrong at the end of it, right? So how do you do this? So how do we figure out the most probable word sequence W star given the X, the acoustic features, and the word sequence, and the possible set of word sequence, right? Find out those from the vocabulary and find out which is the most likely. And it looks like really enormous task. I'm not sure whether you agree with me or not, but today the ASRs does it in a blink of an eye. You finish speaking, it spits out the text. So it's so much efficient it becomes. But now we're talking about the traditional approach, right? The traditional approach, the principle of the traditional approach, which is the left column of my summary slide, is that you break this down into factors and then try to optimize each of those factors. So what are those factors? Let's use Bayes' rule, right? So if you use Bayes' theorem, the P of W given X, right? Probability of W given X can be written as probability of X given W times W by probability of X. Now you see we are searching for W. So if you go to the previous slide, what is our optimization on W? So in the numerator you have W, but not in the denominator. So you don't care about the denominator. So you just say, well, that means I can replace the previous optimization problem, this one, with this. Now this is the another key reduced version of it, right? And there is no loss. So what you would have got here is identical to what you have to get by solving this as well. So what are these two components? So this P of W is the likelihood or probability of words. So this is called language mode, right? What is the likelihood or probability of a sequence of words? Let's say, I eat computer. Very low likelihood. We know never eat computer, right? If you go out and find out text, and then find out what is the probability of this, how to compute is a different question. But what is the chance of it? You say very low. So in no way you should be spitting out I eat computer for a, right? Some other thing maybe, right? Now, what is the other one? It's called the X given W, probability of X given. So this is saying the acoustic model. So it says what is the probability of a set of feature sequence given a word. So if I say a word called sun, given that word is sun, what is the likelihood of a sequence of MCCs? Can you compute that? If you can compute that and compute this, then what you can do, you can choose a word or a word sequence and compute what is the acoustic score or likelihood or probability for the given observation or feature sequence. It's called observation, feature sequence, audio, for that sequence of words, and also compute the language model score, which is the likelihood of those sequence of words, and then multiply them and find out which word sequence gives the maximum. But the challenge is we don't know the length of the word, number of words, right? Because we are given only samples, we don't the audio samples. We are not told there are 5 words in it, right? Right? If there are 100,000 words, then 5 words will mean 100,000 power 5. This is an enormous search. How do you really take care of all that? So if you look at the diagram on the right hand side, this is a pictorial summary of what is on the left. So this is the raw signal. You compute acoustic features, right? These are MCC features, and you build acoustic models. So you know that for this word sequence, this is the acoustic model. This is the MCC sequence. But we know we don't operate in word. We operate in triform. So from this, large amount of speech signal, you figure out for each triphone what is the X, how does it look like. So this W need not be word, it could be triphone, right? And then we can see how we can go from triphone to the words later. I'll come there. So once you learn this acoustic model, which is chance or probability or likelihood of a feature sequence for a given triphone or sequence of triphone or word or sequence of word, right? That's your acoustic model. On the other hand, the language model use a lot of text only. Need not be the text for this sentence, but just text from anywhere. And with that text, you build the probability of the word sequence, right? And of course, while learning the acoustic model, because you need triphone, you need the pronunciation dictionary, what we talked about, right? RT meaning or A, R, T, I, Y, right? So in this case, don't you understand me? Will be broken down into the corresponding phones. Then it can model the OW phone in the context of D and N. That's a triphone. Or the N in the context of OW and T. That's another triphone. So you can find out which part of the audio corresponds to the N with this context, so for this triphone. So for all the triphones, you can learn the acoustic model. And from all these words, it can learn the language model. And then together, it can compute for any new acoustic uh, feature sequence. It can compute this code as well as this code for all possible word sequence and then find the one which is max. And this is the crux of the entire ASR, whether it's a traditional or the. So, of course, in the traditional case, we broke it down, right? But we need not break it down. We can do something else to talk about in the interview. Okay. So, now let's see. So, now here, I just want to highlight the challenge here, right? So, let's say, as I told you, if it is a 20 millisecond segment with a 10 millisecond shift, in 1 second you have 100 different features. So this capital T for 1 second will be 100, right? 13 dimensional, 39 dimensional feature, MCC 13, delta will be 39. So we have 100 39 dimensional vectors. That is your input. But the output will be in 1 second how many words you can speak or how many triphones you can speak, right? Whatever way you take it up. It may be 10 triphones. I mean, you can't speak 100 different sounds in a second, right? So this T is typically much greater than N. So it's a sequence of MFCC features as input, which is really large sequence. I have to convert it to a smaller sequence of words or type. How do we do that? And that becomes the biggest challenge. So maybe even if we go to the individual triphone level, that's what the benefit is, as we talked about. So what he said is, well, instead of the words, let us bring the phones in the picture now. In the probabilistic formation, we have been thinking, but how do we bring words to phones is the connection here now. So, well, why don't we, marginalize over all possible pronunciations of these words, right? And then have the joint distribution or the joint likelihood of x. Well, you don't have to compute joint likelihood, you can factor it out. P of x given s times p of s, correct? So this is now, if you call this to be a triphone, then you can have acoustic model, which is only built on the triphones. And you can have a pronunciation model, which is for this word, what are the triphones, or what are the phones, right? If you take S to be phones, it can be for each phone, what is the likelihood of this feature sequence, and what is the likelihood of the phone sequence for that word, right? So you are breaking down word to features via phones or via triphones. Right? So this part, as I told you last time, is the acoustic model, so it is taken care of completely by the acoustic model with these parameters. So you learn now some model that is parameterized. You learn those parameters from the data, right? And these are language models. So they'll be for the parameter for the language. So these are the two sets of parameters, theta A and theta L, acoustic model, and the language model. But who will help us? How do you develop this model? What is that model? And there comes this HMM as a rescue person. So HMM, which is hidden Markov model, helps us to model this time series. See, you have to model, we have to take care of the sequence of features. It's not that I give you a feature and you match with the feature, right? It's a sequence of analysis. So the way it is done is the following in HMM. So HMM has two parts. One is the hidden part, which is the Markov chain, and this observable part. So you are at the one of the hidden parts with some probability, and at that part, at that state, you emit some observation with some distribution probability. Okay? So the underlying hidden structure is controlled by the Markov chain, correct? And then, of course, you have the initial probability distribution, and then at each state, and of course, you have the transition from one state to another, and then finally, when you are at a particular state, you uh, emit the observation based on the emission probability. So overall, in HMM, there are three main things. One is the initial state probabilities, which state to begin with, then in which state you traverse with the state transition probability, and at a state with what PDF or probability density function you emit or you realize on. Now, this is super fast for HMM. Okay, you have to really spend time. If you know HMM, that's great. If you don't know, that's fine. You can learn it, and there are references here, so you can do that. Right? So you understand that HMM does a specific way of modeling the sequence of MCCs. That's how you take it from this talk if you don't know HMM, and go back and read it. So together, these three parameters are called lambda. So HMM has a bunch of these parameters. They're all together called lambda. So what we say is the following. We say, well, so let's look at now in our expression of a probability of x given w, that's the acoustic model. We have this x given s and s given w, right? So how do we now compute this s given s? So assuming that these states are this triphone, right, for which the HMMs are built, you assume the conditional independence. That okay, if I know, again, be very careful. So the observation at time t is dependent only on the state at time, not the ones before. But ideally, you can take a lot more, but it'll make this very, very, very complex to train. So this is your finally the emission. So you try to model this with your emission density, which is probability of a feature vector if it is at a state, right? So and it will become abstract to you now if you are not knowing HMM. But to give you a simplest idea, for example, you are speaking the sound like cat. So you will be, think of this, you will be at a state for ka, at a state for a, and a state for ta, right? So when you're at ka, the kind of sounds you'll generate is specific to this. When you're at a, you'll be generating sounds specific to that a. And when you're at ta, you'll be generating sounds specific to that. So when I give you a sequence, the MFCC feature for a won't look like same as that of ka. But the question is, can you use HMM to figure out which features are for ka, which features are for a, which features are for ta? And that's what HMM does by modeling modeling the state-specific emission probability densities using GMM. And that's another big monster to understand. Okay, GMM. Okay. And there is a compact, expression for GMM. It's a mixture of Gaussians. It's a probability density function with mixing parameters and the component densities which are Gaussian. So you use, now come back here, you use emission distributions or density function which are GMM. Transition probabilities are, of course, there are finite states. As I mentioned, there are two states, and the initial probability. So these two together creates all the parameters, and then you learn these parameters from the data, right? Of course, talking about the transition probabilities from one state to another is captured in the next term, right? P of s given w. And here also we assume conditional independence. We assume that the state at a particular frame or segment is determined only by the state of the previous state. So if you are at, let's say, ka, right? This is ka, a, t, right? This is sound cat, and there are three phonemes. So if you are at sound ka, what is the chance that you'll move to a, right? For ka, you have to spend some time. There will be some feature. So what is the chance that you'll be staying in ka in the next frame? And what is the chance that you'll move to the a in the next frame? So of course, the staying back is higher, right? Because you have to have few frames within this ka sound, and less probability to go to the a because it has to transit only one time. So a cross phoneme transition, a triphone transition, is less than within state transition. Right? So that's how you build this state transition graph. And finally, when you have this all set up, what you do, you say, well, I have now this, or I have to optimize this parameter. So I give you these MFCCs, I give you the word sequence, you convert this word sequence to phoneme sequence, and then you use phonetic HMM to figure out which HMM states to lie at what frame index or segment index, and what is the parameter of the Gaussian which overall will maximize the likelihood of the observation. And that's a huge training task. And you have to read it. For example, a good resource for that is right here in the reference. And this is typically done in a single word by called Baum-Welch or Vitellio. There is an iterative step. Here is an example. For example, these are the acoustic features, right? X1 to X8, and here is the scat. You have to figure out which frames correspond to, or which feature sequence or which feature vectors correspond to K, which are for A and which is for T. So here it looks like, start here, and then there are these 4 features which are for K. These are for, 2 feature or 2 frames for A and 2 frames for T. Now, this is one such. There can be many such paths, right? You can spend the entire thing here in 7 states here, and then you can move at the last state, you can move both the other phonemes, but that is highly less likely. So which one is the most likely? How do you find it out? And that's all about in the Baum-Welch and Vitellio. So now coming back to the same, now we have sort of got an idea how to train this acoustic model, right, with HMM, GMM, and so on. How about the language model? If the language model is trained with enormous amount of text data, and you say, well, what is the probability of a word, given that I've seen few words in the past, right? This is how autofiller works in your Word or Gmail and any other places, right? So if you have already typed 5 words, what is the next word? You can predict it, right? You can, for example, if I say, before I went to, it should be at the school or market. You can't say before I went to book. Book is not likely at all. So how do you find out this? You actually go and find out how many times when I have seen before I went to, and what is the word that has come? Which word is most likely? So you can count and divide by the total count. That will give you the problem. So that is called the language model. It's called the M-gram language model if you are using M words in the context. Okay? So we now know acoustic model and language model. By the way, each of them has enormous variations and a lot of literature, but I'm not really going through it now because it's time. But I want to give you overall impression, right? So we have now how do you decode it is the question. How do you decode meaning? I have a way that if you give me a sequence of words, I can tell you its probability using language. If you give me an observation, rather sequence of features, and a sequence of words, I can tell you the acoustic likelihood. But how do I now find out this? So I have to search over all possible words, right? Given a feature sequence, I have to find out, okay, if I take I go to, or I went to, or I will go to, like there are many 3-word or 4-word sequences. I don't know the number of words, so you have to really search for over enormous word combinations. And that becomes a humongous task in terms of if you do an exact search. It's not possible. So the VTRP decoding, which was motivated by dynamic programming, it simplifies life. It computes this exact search in a much more efficient way. But again, it's not possible for large vocabulary tasks. Why? If you look at this, think of this here, where it is, here, for example, right? Suppose here on this y-axis, instead of phones, I have triphones, right? We know it's 38 square, so it will be huge set of possibilities on the y-axis. On the right-hand side, it will be, let's say, 100 frames for 1 second. Now, how do you find out the best path? It is a humongous search. And if the number of words is on the y-axis, it will be even more bad, right? So there are many ways, by the way, to reduce the complexity, including beam search and so on and so forth. But what has come recently, very trendy and useful, is called weighted finite state acceptors and transducers. So these are machineries which accept valid sequences and reject invalid sequences based on your observed data. And transducers are which accepts the input sequence which are valid, but also at the same time emits the corresponding output sequence. You can think of giving acoustic feature sequence as the input, and output is the word sequence. So the WFST is the machinery through which you perform what is called the decoding of the HMM. So when I say decoding of the HMM, it means through HMM, I have already learned this P of x given W, and this is language model, right? We have already trained those two. Now you put everything into WFST. And how do you do that? So for that, you have to understand WFSA and WFST. But essentially, to tell you in a quick and short phrase, as I told you, it accepts the sequence of symbols as per the probability or the likelihood of that sequence, right? And what is interesting is that you can represent both the HMM, the phonetic state transition of the HMM, as well as the grammar states or the language model, all under WFST. And more importantly, the WFSTs can be combined. They can be reduced, minimized, and determined, right? So all of that together helps to really compactly represent the acoustic model and language model through WFSTs. In particular, there are 4 WFSTs that are typically done in HMM-based paradigm, which is called the HMM states, context-dependent forms, pronunciation, and the word level grammar, which is the language. All of that, you create 4 different WFSTs and then compose them, become one WFST. And to that, you give the sequence of features and you get the sequence of words. Looks like quite, I'm going too fast. I have to go too fast for this now. But if you're interested, read this reference, right? So I'll move on. Now, once you get the given a feature sequence, you let's say get the word sequence out. How do you know how accurate you are? So there has to be some metric, right? What is called word error rate. What is word error rate? Let me give an example. So here, so it is computed using number of insertions, deletions, and substitutions. So I is the number of word insertions, D is the number of deletions, substitutions. So let's take an example, right? Suppose the target was the cat's at on the hat. Suppose, right? But here, sorry, I think I made a mistake. So the cat sat on the right. So the ground truth was the cat sat on the hat, but the prediction was the cat sat on the mat. So what has happened? So it has all the words identical except the last word, right? It has substituted hat with the mat, correct? So you see no insertion, no deletion, but only one substitution. And n is what? N is the total number of words in the target, which is 1, 2, 3, 4, 5, 6. So n is 6. So it will be 1 upon 6 times 100, which is 16.67% word error rate. But suppose the again the cat sat on the mat, but the prediction was cat mat. Then you see what has happened. So you deleted the, at, on, the, right? So there are 4 deletions. And then there are 2 substitutions. You know, here cats became cat and hat became mat. So it is s equal to 2. So it will be 4 plus 2, 6 divided by 6 times 100 is 100% order. So you get a picture, right? So the output of the ASR, it may cause all these kinds of error, insertion, deletion, and substitution. And this is how you combine all of them into single metric called word error. And there are many other variants, character error, letter, match error, and so on. If you're interested, you can read this. So that's great. So we are sort of done with, one part of the story as to how do we use GMM HMM framework with language model with WFST machinery to figure out what is the word sequence given the features. Now the question is, how does deep learning come in, right? So when I look at, so what you saw, right? This emission probability was modeled using GMM, but it can be very well done using DNN. And why? See, the GMM is a strong assumption. So you assume that the distribution of these features are Gaussian-like. But what if the features are not Gaussian, right? So DNN do not go by such restrictions. So it has the flexibility to train or learn any kind of functional mapping. But the question is, how do we train a DNN to model this xt given st? So for a given state, how do we learn the likelihood of the corresponding features? Not possible. So we do a trick. We use what is called hybrid approach using pseudo-like. So we use again the Bayes rule to write this as st given xt, because st's are finite, right? They're discrete. They're triforms, think of, right? And xt is the MFCC feature vector. So we can compute a classification task, right? For a given feature vector, which phone sequence it is, and then you can put a neural network. Given an input feature, tell me which triphone it is. That DNN can generate a likelihood and divide by P of st, but that is a prior probability of this state, right? So this is how it goes. So DNN, for training the DNN, you have to train the DNN. So you need to figure out which frame corresponds to which state, and that comes from the GMM HMM algorithm. So when you train the GMM HMM, you automatically figure out using Baum-Welch algorithm which segment correspond to which triphone, or the state of the triphone. That you give as the training data to the DNN. And then in the decoding time, and this output, the target can be, as I've been telling always, phones, triphones, or triphone states. So this ST can be any of those things, and there are results of very deeply using all of those. So then you train the the DNN with that. Then what it means? So in the decoding time, you get an XT, which is the feature, MFCC feature, you give it to the DNN. It tells you which triphone is most likely, right? And it does a lot better than GM. So to give a concrete example, right? You can use a lot of these tools, HTK, Finks, or Kaldi. Kaldi is this link. You can go there. It's freely downloadable link. Go there, download the Kaldi toolbox, and run on this freely available 500 hours of database called Common Voice by Mozilla. You can run it if you have sufficient and good enough GPU machines. Then you can get a WLR rate up to 4.8%, which is very good. That somebody speaks. So essentially, there are training and testing set in this voice data set. So with this Kaldi TDNN model, what is TDNN? I'll come in a bit. It's one variant of DNN, by the way, deep neural network. You can get 4.8% order, which is quite impressive. Now, what is TDNN? So as I told you, right, TDNN or any DNN, what it does, it takes MFCC features input and tells which triphone it is most likely, or tells the likelihood of it. So what it does is it doesn't take only one frame MFCC. It takes few MFCCs before and few MFCCs after. So this is called T minus 13 to T plus 9. So it takes 13 frames before, 9 frames ahead. And then as you see, these are linearly combined with a nonlinear function and goes here, right? So there's a 5 context. You put the context of 5. And then you look at the gray plot, not the red first. So you combine all of them every 5 year and go to this layer. Again, here you combine 4 of them and go to this layer. Here you combine 4 of them, go to this next layer. And then you combine 7 plus 2, 9 of them, and get one likelihood, right? So and this is a 4-layer DNN. But people have shown that you can perform subsampling. What does it mean? That you don't have to really connect all of this. You can only work with these red colored ones, and you can get the same accuracy. And there are also wait time, meaning which is typically done in CNN, you may know. So the wait on this branch is same as the wait on this branch. The weights are tied so that the number of weights are effectively less. So with all of that, TDNN shown an enormously great promise, and TDNN best Kaldi recipe, as I showed you, gave the best performance. If you're interested about that, you can go and read this for more details. Okay. So with that, we are sort of done on the traditional part, and you saw how deep learning came to compute only the emission probability part, substituting GMM, but the rest of the machinery remains. Language model, pronunciation dictionary, WFST, everything remains. Just DNN comes to compute the likelihood. So I hope that is clear how DNN comes and creates contribution. Now let's come to this end-to-end approach. So what is the difference between the traditional approach and the end-to-end approach? Okay. Well, I can take some questions, but I believe we are ending in 10 minutes, right? So probably can take all the questions at the end. So let me go to the ski slide again, right? So here, you remember in the traditional approach which we talked about a while ago, we broke this down into using Bayes rule. But here, end-to-end approach says we don't really worry about Bayes rule, because once you go through Bayes rule, you need to have pronunciation dictionary, right? One word broken into phonemes, because that's the pronunciation model, and you need to take care of the emission probability anyway, which is taken care by DNN. But how do you combine all of that directly optimize? And how do you do that, right? That's the big question. The way to do that is the following. First, you have to determine, before you do that, you have to figure out what is the input and output here, what you're trying to map. Is it possible to do end-to-end, meaning speech to the target output within one network, right? So here, typically, although there are many possible outputs, phone, triphone, characters. Now you can use characters here, right? You can say, well, I want to directly spit out the English characters with the input speech. This is a mapping of a speech to the English characters. It has been found out that the characters or character engrams have been most effective so far. And if you jointly optimize, you really don't need, as you see here, alleviate the requirement for the pronunciation. The pronunciation is a big task. Whether you speak schedule or schedule, you have to really write them down. Okay. But here we don't need any of those. It's directly waveform to character mapping. Of course, it has this flexibility benefits. I'll say that it can do faster processing because it doesn't have the lexicon or things and could be higher quality. But of course, nothing comes free. You must guess what is the problem here, but we'll see in a minute. So how do you do it, right? So in the traditional approach, HMM was the key. Very important, right? You understood that. So on the end-to-end approach, an equivalent of that comes from CTC and attention. I'll talk about both of them, but very briefly. What is CTC? So the CTC helps in training, RNN with, label unsegmented sequence directly. See, when for example, when I give you a sequence of feature vectors and you say you have to map to CAT cat, right? So the input is sequence of feature vectors, MFCCs. Output is 3 letters cat. How do you know which feature to map to what? Right? So that is the first question to answer. So question is, can we do this? For example, I say, well, first 3 are for C or 2 are for C, then A for 3 and T for 1. But who will do this job first? You have no clue, right? Nobody can hear and say, well, the first feature is for, and that will be enormous task. So even if we do that, it has 2 problems. Why? For example, what about repetition of the character, right? Hello. There are 2 L's already in the English character. And they'll get confused with such repetition in this, naive alignment. How do you decipher that? And more importantly, how do you take care of the silence in between words, right? Suppose you say the cat sat, right? So there's a gap, and there will be a form itself within. How do you take care of that? So the beautiful contribution from CTC was introduction of a blank token. How does that work? It's like this. So you say, well, I have to map this feature sequence to hello world, right? So spaces are the silences between words are taken care of by the underscore. And there is a blank character or blank token that is used for taking care of this letter to frame mapping or segment mapping or alignment. So you say, well, if there are 2 L's, as you see here, right, there is a blank character in between. So the L's are now separated. So now this blank character will keep a distinction between. So essentially, these blank characters are dummy characters. They are not used in the loss function, but they are used to just make sure that we don't lose track of repetitions of the characters. But that brings other problems, and they're good or bad. So, for example, you can now insert this blank character anywhere, right? The hello can be this or this. So essentially, for hello, there can be many character sequence, or this, we call it the predicted alignment, that can correspond to hello and this frame. Which one will you pick? And of course, that there comes again the alignment problem, right? So this alignment, we have to be done over all the possible character sequence. Again, for the alignment, we have to work out, again, this conditional likelihood has to be maximized. And to simplify that, we go down to the individual token level and put conditional conditional probability assumptions so that things become much more simple, right? Otherwise, search becomes, so again, essentially here also you do a similar kind of search, but within the neural network paradigm, right? So you have the feature sequence with this, if you have to map to AB with the blank token in between, and you ask which frame to go where, and later on you throw away the empty tokens, right? So here's the loss function for CTC. It's essentially the P of y given x, as we computed here, negative of that. So you minimize this loss, right? And well, there are plus and minuses. First of all, the independence assumption, makes the performance of the CTC kind of poor, but of course it makes it fast. So the first time CTC was used on timid phone recognition task in 2013, and that was one of the first work that showed where you can directly use an end-to-end approach for doing the phone recognition. That was really great. It used unidirectional, bidirectional RNN followed by CTC, and in particular, what was very effective for that training, I must emphasize that there are two regularization techniques. And you realize that for DNN, regularization is a must. Why is that? Because without regularization, the words will go crazy. Right? So there are two techniques, which is called weight noise and early stopping. You can read this paper and get more clarity on those. Without regularization, the training goes everywhere. Now I have to give you some examples of several end-to-end approach for speech and some of the ASR that are out there in the market. For example, the deep speech you might have heard about, right? So it is trained with 5,000 hours of data. Now, why this much of data? Because this network is now humongous. So the data, the network is humongous. You need enormous amount of training data to train it. If you don't, the network don't get trained well. And you have to really tune it and monitor it very well during training. Otherwise, it doesn't get trained well, right? So it has, of course, a lot of advantages. It uses language model as well, right? But few of the errors still remains. So what they did, they worked for the next version of the deep speech. It's called deep speech 2. It has 35 million parameters. Huge training data, right? You see the architecture, right? As I told you, it has CNN, RNA, and then you have this fully connected followed by CTC loss. But it was great compared to DS1 because it reduced the order rate big time and also speed up by 7 times. Again, you can read this paper for more details. There are other networks like wave to later or wave to later plus, right? So there are varieties of networks that has come with end-to-end approach, but all of them has this demand for a large amount of data and also has clever and tricky training. And you need, of course, humongous amount of compute power, a lot of GPUs, machines, and so on, which today on the few places can do at this point. And we are expanding, of course. And there are various extensions to CTC as happened, gravity CTC and other extensions. You can read about this again. So I try to make sure that I leave references there so that you go through them. Of course, I'll share the slides. Okay. Now comes to sequence attention, which is very short. I did not do so. This attention approach is another where it models the P of y given x, or rather optimizes this with the assumption that we model this condition on the previous frames and the on the previous frames y and the input. So you say, well, what is the likelihood of getting a particular character out at this frame, given that I have seen this acoustic data and also predicted the characters in the previous frames like this, right? That will determine or give more. And there's the attention-based objective function, which you can see in these two slides. And there are two kinds of attention, primarily content-based and location. Okay. And if you look at this listen, attend, and spell network, LAS, they are based on the sequence-to-sequence approach of the attention. Right? I must tell that this is even more difficult to train, more so than CTC. Okay? And it's slower during decoding. When you give a speech and decode, it's slow. Right? You can't do online streaming kind of decoding. I don't really spend much more, but I want to say that you can combine the CTC and attention, and that is what has been done in ESPNet, which is a freely available toolbox, where they use the CTC loss and the attention loss, linearly combine them, and have an overall loss called multi-objective loss. It's called multitask learning. And it has shown to give a better promise than and of course, the decoding requires, again, careful optimization or sorting out things with beam search and language model. And the good part is that you directly get the characters. But of course, you need language model, which you can include it in the decoding. So how about the examples here and the tools, right? I've given you all these links. Please feel free to go to these links and figure out codes that you can download and run in your machine and train. So as you see, going back to the old table and compare, right? I took it from the old table. You see that the deep speech got 5.5% of there. It couldn't beat the Caldi TDA. So you may say, what's happening then? Why did you go for end-to-end? So here is a word of caution. So you must remember that in Calditarian we needed a lot more resources. We needed an entire lexicon, which has the word followed by phone. That was not needed at all in N2N. In N2N, you had only the feature sequence and the word sequence, or the letter sequence, right? That's nothing else in between. So with that, without using any lexicon, it has got to 5.5, which is quite impressive. That means we don't need really hard work lexicon or pronunciation model. But of course, you pay a price. You need a lot more hours of data. So if you use more data instead of 500 hours, you get better, right? So with that, I would like to stop with a quick summary. So I hope you got an idea, right? The deep learning paradigms contributed in a large way in the end-to-end and in a little way in the traditional approach. But there are many systems still that are being used in the traditional approach, particularly because a lot of training data is needed for it. So I'd like to conclude with this summary. Sorry, I've taken 4 or 5 more minutes. So what we saw today, understanding ASR, its potential use and growing market. And we saw what are the features and metrics to compute. We saw the statistical approach to speech recognition, particularly the probabilistic approach, including the acoustic lexicon and the language model. And we saw mechanism for this end-to-end network as well, with CTC and attention. We have come to know some tools that are open source, like Caldi and ESP.NET, that you can download and try and train in your machine if you have training data. And of course, you can get the data from OpenVice, which is freely also available. And we have now seen also a few examples of the state-of-the-art ASR system, like deep speech. So with that, I'll stop and I'll wait for questions. I'll certainly share the slides. I see several requests on the chat, but if you have questions, please feel free to ask. With that, I'll stop here. Thank you.
Sir, there are a few questions in chat window.
Okay, please go ahead.
Can we use lifting wavelet transform for feature extraction?
Yeah, I think I answered to that during the MCC itself. I saw that question. So you can use many other techniques for computing features, but typically it has been shown that MFCC performs the best so far.
Okay. And there is one more. UI UX design research problems.
What can the questioner elaborate on that? What do you mean by UX UI design research problems?
So this is from Kanchan Katake.
Can Kanchan speak out?
Yes, I had the question in that. I had posted in the chat.
Yeah, so can you elaborate on what do you mean by UX UI design research problems in
Actually,
this
I
context?
saw the you presenting upon the voice based and all. So like applying AI on voice based. So like I was planning to work in that area. So like improve the user experience. So what are the things we can like work upon or like latest trends like voice based or any way which we can enhance the user experience. So I was thinking for research in that area. So that's the reason I was asking.
Yeah, see, typically what has happened is if you directly, use this ASR based on the models and then ask to recognize somebody's voice, it will go wrong. In many times, right? It will not be always correct. What happens when the user experience comes? That's a different dimension altogether. If there is a mistake by the system, and system doesn't have the capacity to adapt to the user, then the user gets fed up with it. For example, you keep on asking Alexa to show some or play some song, it can't understand, and it become really irritating. So what happens is, in many systems, I have seen that when the ASR recognizes, then they ask, did you ask, or are you looking for a song, or is asked back. But then the answer to that yes or no is easy to recognize, because you know that user will say yes or no. So you bring some kind of interaction with the user to make sure that it's not a one-way communication, right? You have to ask back. If that happens, then the user feels also connected. It's not a machine anymore. So that way the user experience becomes better. That's one. Second, when let's say you recognize, typically these systems, they don't recognize only the best sequence of words, right? The W star I talked about. So there'll be next best, second best, third best. You get many of them. So you often present all the outputs on the screen depending on the application. So you say, well, did you speak one of these? Then the user directly taps. For example, I'm writing a book, right? And I want to speak and I want the computer to type out. That requires, it's called a dictation system. Now, I speak a sentence and the computer or the ASR system could not exactly get it, right? So maybe there are quite a top few highly competing likely sequences of words. So it spits out all of them. So that did you speak one of these? Then it's easy for me to go and click and choose the right one, right?
Yeah.
So these are ways to enhance the user experience when you deal with success.
Sir, do you think there is scope for research in this?
Oh yeah, there are a lot of people working on this part, because without this, nothing will go in the market, right? When you have to deploy such technology in the market, you have to think about user experience. Otherwise, people just don't buy your product. So there are enormous, work even in that
Because
direction, which I
I'm
didn't cover at
currently
all.
taken admission, and I was
Sorry?
like, currently I have taken admission for the PhD, and so I'm looking for a topic, and my guide suggested me to look in this area. So that's why I was thinking that through the FTP I will gain some insights like
Yeah,
applications and all.
absolutely. I mean, you can. I didn't put any reference in that regard because I didn't, put my flavor of the talk in that direction at all. But yeah,
Yeah.
I mean, there are a lot of work in that direction. You can Google it out, Google Scholar it, find out. There are a lot of work in the UI and UX direction for ASR in particular.
Okay. Okay. Thanks a lot, sir. I
No
will
problem.
connect with you if I have any doubt further.
Absolutely, no problem. No problem.
Thank you.
Yeah, I see another question. How different is extracting image from database using image and then use speech so we have meaningful outcome? I'm not sure whether I understood, Abudai. Can you speak out? What do you mean by?
Yes, hi, good morning to you. Am I
Oh,
audible?
yeah, sure. Go ahead.
Yeah, so basically, I want to ask is that if you can compare the two inputs that you have for the database, like images, and then you have the speech, you're trying to extract the same content from the same database, but somehow because the UI that we are developing on this planet, also all highly biased towards the images. So, is it more meaningful to work on the speech? Can you give some idea about these two inputs?
So, if I mean, let me understand your question better. So, are you saying image to Abudai, are you there?
Yes. Please repeat. There was some.
Yeah. So, if you are asking for whether we can given an image, right? There is a corresponding speech text that you want to generate. Is that if you are asking that, that's a different kind of problem, and it is really there. For example, I give an image of, let's say, a horse is grazing, right? Then you have to come up with a sentence for that image. So this kind of task is present. And in fact, if you see this end-to-end architecture I showed you, deep speech, right? See, it works on an image, which is spectrogram, and then generates the output.
Mhm.
So you can always do such training, okay? And people have done it already. But what we talked about here is more from audio files to text, not image to text. But of course, you can take an audio file, convert it to an image like the spectrogram, and then from that image can go to the text also.
Oh, no. Okay, that's great. But then I have another question. That same thing, if the searching the content you're doing with, instead of speech, you have the image. Okay, so instead of speech, you have the image, and still you are trying to search the content,
I
the
see.
relevant content.
I see. Okay, so you're asking for image search in particular.
Yes.
Yeah, correct. Yeah, see, the image search work in a different way. It does not. I mean, so the
Okay.
search is different altogether. So for example, let me ask you. See, so suppose I speak. I want to find out weather today, right? So I type weather today, and then ASR converts it to text and search in the text. But when I want to give an image as a search, it does not work in this
Yes.
standard ASR approach at all. It's a different altogether story. So it's called image retrieval, right? You give an image, and from the pool of data or the billions of images, you have to find out. So those are typically done by a different kind of network, not this. So that's a different problem altogether.
Okay, okay, sir. Thank you very much, sir. Thank you very much.
Okay. Yeah, I see the next question. Can you use OpenSmile software for real-time voice data? Not clear. What do you mean by real-time voice data, Dr. Manju?
Yes, sir. Good afternoon.
Good afternoon. Please go ahead.
Sir, the OpenSmile software, like I mean to say, real-time voice data means like how I'm explaining now, right? If I'm talking now, can it capture that particular data and can it do processing on it?
See, to capture your speech that you're speaking now, you can use many other softwares, not OpenSmile. OpenSmile is used to extract features on the recorded audio files. So, for example, you can use simple Audacity or Pratt software or any other recording application software. And as long as you have a sound card in your laptop, you will be able to record that with some decent quality. Once you have the audio file, then you give it to OpenSmile. It extracts features for the given audio. So the recording and feature extraction are two different things. Recording has to happen with recording software. OpenSmile typically is used for feature extraction.
Okay, fine. Thank you, sir.
Thanks. Any other questions?
Sir, I guess no more questions from participants now.
Okay, great.
Okay, so we are at the end of the session now. So I thank Dr. Prasant Ghosh for sharing his insight on deep learning for automatic speech recognition and also providing applicability of the technology in various sectors. I thank you so much for accepting our invitation, sir, and getting associated with this FTP. It was an excellent and informative talk, sir. And we look forward to more such associations with you again. Thank you very much, sir.
Absolutely. All the best to all of you. Thank you.
Thank you, sir.
Thanks. Bye.
Bye, sir.
Ma'am, what is the next session timing?
Next session, it is at 2 o'clock.
Okay.
So it is the last session of the day. So it starts exactly at 2 o'clock. So we will join for the next session at 2 o'clock. Thank you.
Thank you.
गए 4 7 4 4 3 से 12 7 ठीक है। अब ये हो गया 19 species of the stage of हेलो। हाँ यार रात को पहुंचे थे। रात को ना वो पता है क्या हुआ, जाते वक्त ना 6-7 घंटे लगे थे। तो हम इसी चक्कर में बैठे थे कि आते वक्त भी 6-7 घंटे लगेंगे, सुबह सुबह पहुंचेंगे। और भाई साहब उसमें पहुंचा दिया रात के 2 बजे। पता नहीं कैसे 4 ही घंटे में पहुंचा दिया उसने। अब जाते वक्त नहीं लगा, आते वक्त जाते वक्त लग गया, आते वक्त नहीं लगा। तो अब उसमें 4:30 बजे का ठंड इतनी ज्यादा थी। अब हम बोले कि बस स्टैंड बैठेंगे, 2-3 घंटे और बैठना पड़ता। 4-6 बजे से पहले बस ही चलती। तो बोले चलो घर चलते हैं। तो हमने वैसे 43 में उठा रहा था तो डेढ़। हाँ तो यही वही किया, कैब बुक करके घर आ गए। और घर आके सो गए, और सो के जब उठे तो 7:30-8 लेट हो गया था। तो फिर भागे भागे यूनिवर्सिटी आए, और यूनिवर्सिटी में आके कॉल अब शाम को करते तुमको। ये पूछ रहे थे उस कुकर का वो डेट बताया कब तक आएगा। सैटरडे तक आएगा ना, चलो फिर ठीक है। ठीक है, कोई बात नहीं। ठीक है ठीक है ठीक है। और बताओ क्या चल रहा है। यहाँ तो वापस तो कोहरा हो गया। हाँ यार, धूप निकला है, लेकिन इतना हल्का धूप निकला है रात की मतलब हल्का एकदम।
तो ल्यूमिनेसेंस पे कर देता।
हाँ ये तो है, मतलब ट्रांसफर सर्विस का ग्रीन है, जैसा ही है वो भी। गंदा रहता है। अब हम इस सेक्टर में पड़े। चलो ठीक है, मैं बड़ा बुरा हाल है यार। नीचे भरे हुए जल में क्या लिखा है? अब मैं बताती हूँ सबको, हाँ मेरी इंटरव्यू क्या आएगी ना, सारे बंदों ने सोना गोल्डी लेके आया उनके साथ। फिर बस ये लास्ट बन रहा है, बाकी सारे बन गए, बस इसको मेल कर दूंगा फिर। ये हो गया ना, उसने भेजा ना यार लोग, उसने वो तो खैर नॉन मेडिकल का है, वहाँ जाएगा ज़्यादा। हमारे और ये फर्स्ट ईयर का तो भेज ही दिया था, ये बीएससी का हो गया। बीएससी के प्राइवेट सेक्टर में 2 ही तो ये करनी है। बीएससी पोस्ट है उसमें, वो सारे एमएनसी वगैरह का डाल दो ना, लाइफ स्किल मेंटरिंग डाल दो एक, सर वो सर्च कर दिया ना, टाइम टेबल में कहाँ जाएगा।
गुड मॉर्निंग सर।
क्या आपने चेंज किया है यहाँ पे, इसको अगर यहीं रख दो तो पहले तो कंटिन्यूस हो जा रहा था, कंटिन्यूस हो जा रहा है ना, एक कंटिन्यूस ऐसे एक यहाँ पे एमसी रह जाएगा ना।
हेलो, गुड मॉर्निंग सर।
ऐसे कंटिन्यूस हो जा रहा है एक साथ, फिर बच्चे फ्री हो जाएंगे उसके बाद, तो ये तो भी फ्री है ना एक साथ से, पहले तो फ्री है, अपना जाके वहाँ पे जो भी करिकुलर एक्टिविटी जो भी होगी वो कर सकेंगे। अब तो आइडल हो गया, सी आइडल भी चालू हो गया, सिंगिंग कंपटीशन बना रही है। थोड़ा सा ना फॉर्मेट का ध्यान रखना, बड़े बड़े प्रिंट आउट नहीं आते हैं ना, और ऊपर जाना क्लास सेक्शन नेम पूरा प्रॉपर है ना, पूरा प्रॉपर लिख देना हर जगह, कौन सी सेक्शन है जो है ना, कौन से फॉर्मेट में प्रिंट आउट लेना चाहता। सर ये बताओ, डिसर्टेशन के स्टूडेंट जो है उनके लिए टेबल अलग चाहिए, हाँ बस उसमें एक ही रहेगा, फिर एसपीटी का कुछ नहीं रहेगा, बाकी डिसर्टेशन एक लेक्चर का वो डालते हैं ना, बाकी डिसर्टेशन प्लान, रिसर्च प्लान। है ना? सर कुछ लोग बोल रहे थे कि ये लैब जो ऐसे चलेगा कि कोडिंग पहले हाथ में रहेगा, फिर मास्टर्स फिर लैब शुरू करेंगे। हाँ, सही कहा सकते हो। हाँ, तो मैंने ऐसे किया कि सारे लैब में नहीं चला देता हूँ, पहले और चला रहे हैं। केमिस्ट्री में उल्टा हो रहा है। उन लोगों का टाइम टेबल भी तो चलो बन जाए, टाइम टेबल फिर समझ में आएगा।
Hello, sir. Good afternoon, sir.
Yeah, good afternoon, madam. Yes, ma'am.
Yes, sir.
Is my voice is audible to you? Yes, ma'am.
Yes, sir. Your voice is audible.
Yeah. Actually, yeah, madam, I could not able to connect with my login ID. There is some problem with
Okay.
that.
Okay, sir. We'll make you as presenter.
Okay. Not an issue because I have login with my students email ID.
Sir, your PPT is visible, sir.
Yes, madam. Yeah.
Yes. Shall we start the session, sir?
Yes, madam.
Yeah. Good afternoon, one and all. Welcome all of you to the day 4, session 3 of our faculty development program on artificial intelligence and machine learning, being organized by MBJ College of Engineering in association with the ICT Teaching and Learning Academy. So now the session will be handled by Dr. Malay Kumar Nath. So giving an introduction to Dr. Malay Kumar Nath, sir. Yes, completed his BE in Electronics and Telecommunication Engineering from BPUT Odisha and MTech in Electronics and Communication Engineering, specialized in signal processing from IIT Guwahati. He has completed his PhD from IIT Guwahati on signal processing. Now is working as an assistant professor in the Department of ECE NIT Puducherry, Karaikal. He has seconded to Asian Institute of Technology, Bangkok, Thailand, for teaching error control coding in the year 2018 for one semester. His area of research is in machine learning and image processing. He has 25 publications in reputed SCI journals and international conferences. He is the co-CI for the project SMDP. So it's really an honor and privilege to have you, sir. A hearty welcome you to the session, sir. We welcome you, sir.
Thank
Now
you.
over to you, sir.
Yeah. So do you start now?
Yes, sir, you can
Good
start now.
afternoon. Yeah. Good afternoon to all. Today I'm going to discuss about deep learning and its application in agriculture. So before starting with deep learning, we'll start our presentation like what is learning, how this machine learning has been evolved, and how this learning process is started from neural network and it gradually evolved to deep learning. What are the number of parameters, how to calculate, and we'll discuss one of the application related to agriculture. So this is my plan of talk. Basically, I'll discuss on learning, neural network, machine learning, deep learning, its application to agriculture, and ended with the computer. So if you look into learning, according to Ambrose in 2010, it represents a process that leads to change, which occurs as a result of experience and increase the potential for improved performance and future learning. So what is mean by machine learning? According to Simon, in 1983, machine learning represents the changes in a system that enable it to do the same task or task drawn from the same population more efficiently as well as more effectively in the next time. And this can be performed by acquiring some new knowledge, acquiring new facts, new skills, and by adopting its behavior. So, as I have, if you look into machine learning, so machine learning is the study of algorithm that improve the performance at some task with experience. And as it is performing certain task with experience, it requires some important information, that is the statistics is coming into picture as well as the role of computer science is coming into picture. Why you should learn this machine learning? Because better we want to develop a better computing system. So for that reason, we require machine learning. That means the machine can learn by automatically, and it can automatically adapt as well as customize themselves. Adapt and customize themselves means take one example of a personalized news or personalized tutoring, etc. If we look into some related disciplines of machine learning, some of the disciplines have been noted down here. Some of them are artificial intelligence, neurobiology, data mining, probability and statistics, information theory, linguistic, philosophy, etc. If you look into the types of learning, then the learning can be classified into different types. And some categories has been noted down here. If you look into induction as well as deduction, the induction represents the